It took me till right now to realize that there's HP on the end of my pen. And I've had this laptop since October.
Okay, we are now recording. So that's the first thing the video will show.
Yes, about how blonde I am.
Okay, all right. Okay, so first time teaching in this setting since 2019. Let's just see what happens, and God help us all. Okay. All right. So this is section 1.3 in the notes. At least during some of my research meetings, I've been running on the board for you all, so it's not as weird as I thought it might be. But teaching 3 classes back to back in a mask, I don't know. And I want to remember roughly a halfway point to take a short break. Let's see, that'd be around maybe like 10 past 3 or something. Okay, so well, any PDE problem we want to solve, we want it to be what's called well-posed, and I'm about to explain what that means. So, such a problem needs to satisfy what's known as Hadamard's conditions. Or well-posedness of a PDE plus whatever boundary conditions it has, which may also be initial conditions if the boundary in question is on a interval representing time. Okay, so what are the 3 conditions? First 2 are certainly expected. The problem must have a solution. So a solution must exist. Second, the solution needs to be unique. And then the third one is less straightforward, but extremely important for numerical computation, actually. That this unique solution depends continuously on the problem data. Okay. So then I have to explain what that means. So first of all, I just need to make sure that certain things here are not written here in these notes, but I want to make sure we get into the notes. Okay. I think what would be ideal is each time I fill up a board, before I erase it, it'd be good to have a picture. Now, I'm perfectly fine with doing it myself. Let's see. But what that means is that if I fill a board and I'm about to go erase it, and I haven't taken a picture, someone needs to yell at me. So, because that would be the easiest way. Like, for instance, after class, if I look through these screenshots, which probably wouldn't take too long to flip through them all and see, oh, here's something I wrote on the board and it's not in the notes. And I can put it in the notes and make sure it gets in there. I mean, also it'd be cool if, or if someone's volunteered to take a picture of a board or erase it and send it to me, or if someone's attending virtually, and they can do a screen capture of their own screen. So I don't care. As long as whatever makes the notes better as we go. Okay. All right. So first, the first two conditions, of course, are pretty self-explanatory, but I want to explain the third one a bit more. What is meant by data? When I say continuously depends on the data, what is the data of this PDE problem? It can refer to quite a few things. It can refer to any coefficients, A alpha, that's how the coefficients were denoted in the various types of PDEs that I wrote down last time, like linear, semi-linear, quasi-linear, etc. Or any right-hand side functions that you have, also known as source terms. It's really just whatever inputs of a problem you have, whatever it is that defines a problem. Boundary conditions, like if you're specifying that the solution U is equal to some function on the boundary, like a Dirichlet boundary condition. Well, what is that function? Whatever you're setting it equal to is something that's specified, known up front, is an example of problem data. So any input of a problem, something that could readily be changed, parameterized, is an example of problem data. Okay, so now that I've explained to you what is meant by the data, now I can explain this third condition more. So, at least informally, what I mean by continuous dependence is if there is a small change in the data, then that should lead to a small change in the solution at most. All right, you don't have a situation where you tweak the data by a tiny amount, like something along the lines of round-off error, and then your solution changes by a huge amount. So, in fact, I can relate this to a very important concept that has been discussed in numerical analysis courses. So another way to think about it is the problem should be well conditioned. So that's the definition of conditioning of a problem in numerical analysis or error analysis. That a problem is well conditioned if a small change in the input of a problem does not lead to a large change in the problem solution. And that's an artifact of the problem that you're trying to solve, not the algorithm you're using to solve it. Because you could have a problem that is well conditioned, and if your algorithm for solving it is unstable, then it's still a bad situation, but that could be changed by just using a different algorithm. If the problem is ill-conditioned or ill-posed, which is the opposite of well-posed, that's a terrible situation. Really, you should not bother solving that problem. There's something wrong with a problem that you should try to fix. Okay. So questions about the general notion of well-posedness before I continue. All right. First time figuring out this is the right place to stand. Okay. Chelsea, I want to check this. is writing at least well visible? Okay.
Yeah, it looks good.
Okay. Yeah, because when I took a picture just now, from where I was standing anyway, this side didn't look as great, but I could still read it. So, okay. All right. So, do I not have, oh, okay. There better be a eraser in here. Although I remember telling us that we should like bring our own erasers, but I forgot to do that. But I know that if I bring my eraser from my office, I'll leave it here.
Just make sure you wash your hands really good after class.
Yes, I'm going to have to. Actually, I was thinking exactly that. Although, by the time class ends, I'm sure I'll need a reminder. So I think I have another class after this, and then another one after that. Okay. Let's see. All right, so now examples of well or ill-posedness, because a problem could fail to be well-posed or be ill-posed for violating any three conditions. You might have a situation of solution not existing or not being unique, or not depending continuously on the data. And even with the same PDE, but the conditions involved could cause a problem. So suppose I have a simple PDE. I guess technically this is an ODE. Uxx plus u is equal to 0. Now I can actually write down, I have not specified any boundary conditions yet, I'm going to, but the general solution actually, can anyone tell me what the general solution is? Or if not that, just mention a solution.
Isn't it C1 sine plus C1 or plus C2 cosine?
Yeah, so it's a linear combination of sine x and cosine x. So I can write down a cosine x plus b sine x. Okay. So the values of a and b would depend on the boundary conditions on what, like if we're going to specify this a spatial domain for this PDE. So here are some boundary conditions that I could choose. So option A, I could choose u of 0 equals 0, and then u of pi over 2 is equal to 1. So in that case, what you would do is set x equals 0 and x equal pi over 2 and solve for a and b. And if you did that, you would get sine x. And so in this case, it's well posed. This is the unique solution. All right, so everything checks out in this case. It certainly, if I were to change like one of the boundary values, in like make a small change there, or maybe make a change in, have a coefficient of 1, suppose I change that coefficient, then that would not lead to a huge change in the solution. So, so everything looks good here. Okay. On the other hand, suppose I set u of 0 equals 0, and u of pi is equal to 1. Well, if I set x equals 0 in here, I'm just going to get a. So because of this, A has to be 0. So I'm only going to have sine x. But then if I set x equal to pi, in this term, I'm going to get 0. Can't get 1. So these are, these boundary conditions just won't work. So this problem is ill-posed due to failure of a solution to exist. And it's all because we have plain old sine x. And that's because of the PDE in question. Okay. The third possibility, if I set u of 0 equals 0 again, and then I set u of pi equals 0. Okay, well, because of the first boundary condition, once again, I'm going to have sine. So now I have b sine x. Now I plug in x equal pi. I'm going to get 0 no matter what b is. So b can be anything. So my solution is b sine x for any real number b. It's not unique. It has infinitely many solutions. But once again, an ill-posed problem. We see the effect that the boundary conditions have. Any questions about this example? All right. Here's another example that illustrates a different aspect of well-posed versus ill-posed. All right. So suppose I have a problem specified in these pieces of PDE, boundary conditions, and this would be a time-dependent problem, so also have initial conditions. So the PDE will just be a heat equation. The boundary conditions, so will just be on the interval x between 0 and 1. That's our domain. So the boundary conditions, we'll just say that u is equal to 0 on the boundary, so Dirichlet boundary conditions. Okay. And then for the initial condition, well, there has to be one. Don't need to specify what it is in this case. All right. So there's this problem is one that you dealt with in other PDE classes like 517 or 606. And what you learn there is that you can certainly come up with a solution. The solution is unique. It was a Fourier sine series with decaying exponentials. So a small change in the problem data, like the initial data, would not lead to a large change in the solution. So everything checked out, everything's well posed. But suppose I change the PDE, just the PDE. Ut is equal to minus uxx. And that is known as the backward heat equation. Okay. So this comes about from trying to solve the heat equation backward in time. If I took this equation and I replaced t with minus t, then by the chain rule, we introduce a minus into the time derivative, which I just moved over to the right side in this case. So in that case, we get an ill-posed problem. And really what happens is it is ill-conditioned. So in other words, we do not have continuous dependence on the data. Okay. So a small change in the problem data, such as the initial condition, u naught of x, could lead to an arbitrarily large change in the solution. Now, I don't expect you to just take my word for it. At least in this case, I can write down formulas for the solution in these two cases. I'll do that in a moment. All right. Oh, wait. I'm doing one time here. Okay. Okay, so what does a solution look like? So in the case of a regular heat equation, ut is equal to uxx, the solution has this form. It's a sum with some coefficients a n that come from a Fourier sine series of the initial data, u naught of x, times a decaying exponential, okay, times sine of n pi x. Because if you were taking the derivative of this twice with respect to x, then you'd have exactly this times minus quantity n pi squared. If you're taking derivative with respect to t, then again, you get a factor of minus n pi squared in each term. So it's a solution. And when t equals 0, you get the Fourier sine series for u naught of x. It certainly satisfies the boundary conditions. You set x equals 0 or 1. And here you're going to get 0. So that's a solution, that's its form. So, so if you were to change like the coefficients an a little bit, representing a change in the problem data, because this function is bounded by 1 in magnitude, this is a decaying exponential, it's not really going to change the solution all that much if an is changed by a small amount. In fact, the change in solution for any ever for x and t is going to be really bounded by the magnitude of a change in the problem data. So that's convenient. On the other hand, if I look at the backward heat equation, ut is equal to minus uxx. All I have to do in the previous formula is replace t with minus t. So now I'm going to have exponential growth rather than decay. So what will happen is, if I make a change in an, then for sufficiently large T, that small change in AN can be amplified by a number as large as I'd like, causing the solution at whatever x and t to be incredibly different than the solution before the data was changed. So here we do not have continuous dependence on the data. Tiniest change in the input can lead to an arbitrarily large change in the output. So that's what makes this a ill-posed problem. And physically, it's kind of freaky. Like, you think about diffusion of heat energy, that over time, a heat equation, you have temperature converging to some average. So everything is smoothing out, thus the decaying exponentials. So now imagine from this ambient steady state that all of a sudden you start to have growing changes as you go backward in time. Now, if you're not going very far backward in time, it may not change so much, but if you let it just keep running backward through time, then that heat energy that you're undiffusing, at least in terms of your solution, is going to go crazy. So we definitely don't like to have problems modeling physical phenomena that are ill-posed, because you get some very unnatural things happening. Okay, because you definitely don't want to have in the real world waves propagating with growing amplitude, because that's like some apocalyptic sci-fi movie or something.
Dr. Members, it's 3:11 if you want to take a break.
Yeah, I was planning to right at this point, but yeah, so that'd be a cool sci-fi movie. Ill-posed. Okay, so all right, yeah, let's take a 5-ish minute break. Okay. I don't know if it lets me pause the recording. No, I just start or stop it. So, nope, we're gonna keep recording during a break. Okay. I'll adjourn to my office where I will not be able to enforce the mask mandate.
Ready to go home and take a nap. Are you excited for the training tomorrow? Make sure you do your Unit 2 notes, Robert.
We'll see what happens.
Robert, you're a terrible group peer member.
Oh yeah, she said not to wing it.
She wouldn't know me.
I mean, at this point, who would even be able to tell the difference from Robert winging it or actually being prepared?
Right.
So the half of my first year teaching, I was teaching 12 and 13-year-olds.
Yeah.
Basically I barely ever had lesson plans. I just walked in every day and winged it.
You're like 12 and 13-year-olds do not lead well to a plan.
That's very orange.
Yes. It's also has a lot of caffeine.
That's like cheetah level orange.
It's called Bahama Mama from G-Fuel. It's 180 milligrams in that bottle of water of caffeine.
I was gonna say, I hope there's water in that bottle. Considering it's a water bottle.
You know, I could dunk down and fill it up with orange soda.
Yeah, I'm just thinking about the TV show Kenan and Kel.
I've actually never seen that TV show.
I used to love that when I was growing up. Dr. Lampers is going to hear the recording and hear us talking about caffeine and 90s cartoon, 90s TV shows.
I mean, I know Mr. Carl's already concerned for my heart. Probably knows Chelsea's listening on that.
Yeah, I can hear you.
Yeah, I see. You have snacks and you're not offering to share with us.
Start them off.
I mean, that's a good reason not to share.
Fair enough. Oh, man. Chelsea, sing us a lullaby for nap time.
I don't know about that. I can't sing.
Oh, man.
Yeah.
Well, I guess it's not nap time then. Why are we a bunch of kids?
And everyone in the room currently is almost 30.
Samson, I gotta know, are you older or younger than me?
How old are you?
I'm trying to say.
I'm older than Samson.
I'm
28.
older than you as well because I'm turning 28 in a couple months.
You mean you're younger than me?
I would say I'm older than Samson because he just turned 27.
Yeah.
I'm the oldest. I'm the oldest.
37. Yeah, but mine is 28.
Right. When I was a kid and someone said they were like 25 or 30, I used to think that's so old.
Exactly.
And now I'm just thinking like, oh, okay.
It's like not something I just have feeling because of this, and then I just want to like sit here and mess with the pen all day and not focus on the classes.
I mean, depending on the day, some days it's hard for me to focus on anything. So,
I just realized something that, what I should have done when I went to break was, muted myself. 'Cause otherwise, whatever you talk about is recorded.
Yes, we established that.
Oh, okay. But again, if I don't mute myself, then you're able to chat with whoever is attending virtually. So
so you will hear us in the recording talking about how we're going to be in the recording.
I won't bother listening to it, but yes, I could. All righty. I just realized that I'd taken a little more time than I intended, but for a break. But I don't think anybody minds. Plus, that means there won't be a huge amount that I would cover, and that makes planning for next week easier. Okay,
So confused.
so,
There's a ghost in here.
huh?
Something like rolled across the floor, and I asked Robert what it was, and he didn't know, so I said it was a ghost in here.
Okay, that's not terrifying at all. Okay. Any questions about this?
No.
Okay. And I do a recording, but also I wouldn't want to have to like flip through a recording to find the right place to look for stuff to add to the notes. Okay. Okay. Yeah, I actually had a problem from my NRL colleague during the summer, wave equation, and it turned out the problem was ill-posed, that it produced waves that kept growing in amplitude over time, and that's when he realized that the problem itself was wrong, and he had to change some parameters. Okay, so I've covered that. All right, so now into the next section.
I have questions about
Oh,
like for the Well-Posedness problem,
yeah.
like did the boundary condition change too? It seemed like it did from what you wrote here, you said the PD changed the same condition, right?
Oh, wait, which example are you talking about?
On the notes example 1.33.
Oh, okay, so changing the heat equation to backward heat equation?
Yeah.
Yeah.
The boundary conditions also changed.
Oh, you know
The
what?
two boundary conditions are not the same.
Okay, they're supposed to be the same. Okay, so that's a typo. I should have it equals 0. Yeah, because we're really, the point of the example is to focus on what happens with the PDE. Okay, so good catch there. Yeah, I guess otherwise it would have been not Dirichlet conditions, but periodic. And so then the solution would be combination of sines and cosines. We really just want to focus on what happens when t becomes minus t. Okay. Whoops. All right. So I need to state a definition. Actually, and this definition, unfortunately, is not in the notes. So function u okay, actually going to say it this way. It's that C superscript K which sometimes may be qualified with a particular domain, such as Rn. Okay. Is a set of all functions with at least k continuous derivatives. Now, by default, that's functions of a domain equal to the entire space under consideration. Or if a particular domain is mentioned, then functions defined on that domain D. So C2 would consist of all functions that are themselves continuous and also have first and second derivatives or partial derivatives, as the case may be, that are all continuous. Now, if k is equal to 0, then so this would just be the set of all continuous functions defined on a given domain. But in that case, the superscript 0 need not be written. So we just say C of D is a set of all continuous functions. On D. All right. So this is a very important concept in actually a lot of math courses where it comes to PDEs or real analysis, possibly functional analysis, etc. Any place throughout analysis, since continuity is such an essential concept in all different kinds of analysis. So it's a convenient way to refer to spaces, function spaces consisting of continuous functions. Okay, so now that we have this notation, I can describe the different notions of solutions. So suppose you have a solution of a PDE of order k, meaning that it consists of derivatives or partial derivatives up to and including order k. Oops, k order PDE. So it's considered a classical solution. Sorry. I need to refer to a solution. The solution U. So U is a solution of a k order PDE. Actually, I did not include that in the definition in the notes. That U is the solution in question. Okay. Is classical if U has k continuous derivatives. Now, otherwise, is considered a weak solution. So if you were to take a weak solution and substitute it into the PDE, you would have a problem because you would not necessarily be able to compute the derivatives that the PDE involves. But it could still be a solution in a weak sense, for instance, possibly in an average sense. Certain numerical methods, like finite element methods, are built on the idea of finding weak solutions. Now, the weak solutions in computes may turn out to be classical solutions, but not necessarily. So you might have solutions, for example, that have like a jump discontinuity. So if a solution with jump discontinuity, then you could not compute derivatives at every point, but what you might be able to do is compute one-sided derivatives, like on the appropriate side of a jump discontinuity, and the solution might satisfy the PDE in that weaker sense. Okay. Now, so here are some examples. Okay, so first we have Well-Posedness equation. The Laplacian of U is equal to 0. Well, solution U is one of the properties of Laplace's equation. Is C infinity. It has derivatives that exist and are continuous of all orders. Therefore, this is certainly a classical solution. Okay. Now, second example is a one-way wave equation. So that is ut plus ux is equal to 0. Now, the general solution to a one-way wave equation is just the initial data shifted. And let's assume that the initial condition is some given function u naught of x, and we'll assume it's C1. Well, if the initial data is C1, so continuously differentiable with respect to x or t, so all partial derivatives of that order are covered, then because of the nature of a PDE, the solution is a shift of initial data, and the solution will also be C1. So again, classical. Whereas if U was not C1, then we'd have a weak solution. I'll make that note here. Okay. I'm doing on time here. 3:30. Okay. All right. I think what I'll do, I have a couple more examples. So go ahead and do those, and then that'll be it. So that way, I'm not going to be very far ahead. I mentioned at the Tuesday that the almost all of the homework problems are MATLAB oriented. The exception is the first problem. We're not quite to a point where we'll be ready to do that first problem, but after Tuesday's class, we will cover it up. Or of course, you can peek ahead in the notes. So up to you. All right. Questions about any of these examples so far? Okay. Okay, so far this teaching in the masking is not so bad, although one of your fellow GTAs told me that once you get to the second class in a row, then I'm about to have 3 classes, but at least there'll be breaks in between. Okay. All right, so third example. So the PDE is sort of like a variable coefficient version of one-dimensional Laplace's equation. So we have first du dx multiplied by coefficient b, if it's take derivative with respect to x of all of that, is equal to 0. So if b was a constant, then we'd just be back to one-dimensional Laplace's equation. And then we have the coefficient, however, is discontinuous. So it's equal to 1 when x is less than a half, and it's equal to 2 otherwise. And then we have the boundary conditions. U0 is 0. U of 1 is equal to 1. Now, because of the relatively simple nature of this PDE, what you can try to do is solve it by integration. You can substitute b of x for the appropriate piece for x less than 1/2, greater than 1/2, and then integrate both sides. So for example, b of x ux would be equal to a constant, but the constant may be different for this subdomain versus this one. And then you would integrate again. So then you'd have a linear function on this side, but it could be different for, again, for the two subdomains. And then you make sure that it satisfies these two boundary conditions. And then you would have some arbitrary constants, because you'd have constants of integration, and you'd use the boundary conditions to figure out what those arbitrary constants should be. So what do you get for a solution? So u of x turns out to be 4/3 x when x is less than 1/2, and then 2/3 x plus 1/3 when x is greater or equal to 1/2. Now, if you substitute x is equal to 1/2 in here, so you get the 2/3 in this case, and you would also get 2/3 over here. So the solution turns out to actually be continuous. So then you take the first derivative, and you get the 2/3 over here. No, sorry, you get 4/3 over here and 2/3 over here. So solution does not have a continuous derivative. So this is a weak solution because u is only in C0. It is not C1. Really, let alone C2. C2 is what we would really need, because if you work all this out, you see this is a second order PDE, because this is the same as b of x uxx plus b prime of x ux, or a product rule. So that's why it's a weak solution, even though it's good. So continuity is the best we could hope for here. Actually, just for fun, I don't have this in the notes, but this is show a solution process, because you'll be doing something similar later in the homework. So if I fill in what b of x is, I have ux x is equal to 0 for x less than 1/2. And then I have 2ux x equals 0, x greater or equal to 1/2, just from filling in what b is. So like I said before, integrate both sides, and I get ux is equal to a constant, I'll call it C1 over here. And then I'll have 2ux is equal to C2 over here. And then I go ahead and integrate both sides again. So u is equal to C1x plus C2. And then over here, for this domain, I have that should be C3, distinct from C2. So then I have 1/2 C2x plus C4. Okay. So now, what I could do is, since C2 and C4 are arbitrary constants, and certainly 1/2 times C2 and C4 are also arbitrary constants, so I don't really need that there. Just to simplify the notation. But now what I have to make sure of is that the boundary conditions are satisfied. I plug in x equals 0, x equals 1. So from a boundary conditions, if I plug in x equals 0, I must get 0. So C3 has to be 0. Also, if I plug in x equal to 1, that would apply over here. So C2 plus C4 is equal to 1. So right now I've that much going on. So far, I don't have anything nailing down the value of C1. So what I want to do now is try to specify these coefficients to at least to try to ensure as much continuity as I can. So if I have continuity, oh, okay. So I plug in x equal 1/2 and make sure they match. So u is equal to C1 times 1/2 for the first piece, and then u is equal to C2 times 1/2, and then for C4, that's the same as 1 minus C2. Okay, so so to make these match, I have 1/2 C1 is equal to 1 minus 1/2 C2. So it gives me an equation that that can be satisfied. Okay. So now what I have is okay, C4 is already determined by C2. I have this equation relating them. Although this equation actually would have infinitely many solutions. Now, okay. I just thought of something. And this is what I get for doing things spontaneously. That there's always a chance that things can go wrong. Because if I were to take the derivatives of these solutions, of course I would get C1 for the first domain and C2 for the second domain. Okay. So if I rewrite this, I mean that's C1 plus C2 should be equal to 2. Okay. Can anyone see how I might be able to actually get a C1 solution after all? As in continuous derivatives? Because the derivatives are C1 and C2. If they were equal, then my solution would be C1, not just C0. And it turned out that is satisfied here. If I add these coefficients together, I do in fact get 2. So what if we set C1 and C2 both equal to 1? Then those two continuity conditions are satisfied. But that would mean C4 would have to be 0. So then my solution would be equal to x for x less than 1/2. And then it would be equal to x again assume it's 1/2. So it's just plain old x. That does satisfy the boundary conditions. But okay. I should mention that I got this example from the MIT course, and what they might have been showing was that, okay, the solution shown in the notes, that is a weak solution because it's C0, not C1. A continuous solution of all orders does exist because I could just set u of x equal to x.
But even if this was a solution, it would still be a weak solution, right? Because we need u to be in C2.
Well, but then the solution is always equal to x. X is in C infinity.
X is C infinity?
Yeah. That's a polynomial.
Oh, I see.
Yeah. But what's weird is, like here, because of the coefficient being piecewise continuous, this derivative would not really exist. And actually, oh, you know what? That's the problem right there. Okay, so because suppose I multiply this by b, then I would have 4/3 x over here. And sorry, not, I don't multiply this by b. I take ux multiplied by b. Then I have 4/3 in this piece and 4/3 in this piece too, because I'm multiplying by 2. And now I can take the derivative. So, so an additional constraint on the solution, like to try to have a classical solution, is that whatever you're differentiating here must be differentiable. So it's not just a matter of u being differentiable, b times ux must be differentiable. So if I take this solution, it may only be C0, but at least I can plug it into the PDE and take any derivatives that are required. Whereas with this solution, it's C infinity, but I can't take this derivative. So that's a subtlety there about classical versus weak solutions. So in other words, here we definitely have a weak solution because it's only C0. This is murkier because I can take as many derivatives of u as I want, but I still can't plug into the PDE. So whether it's a classical solution or not, that's something I have to look up, to be honest, to see what to. And because here the definition we're using for classical work versus weak solution, it says, is it CK? But there might actually be more to it than that, especially when you have coefficients.
But shouldn't the solution satisfy both PDE and the boundary?
Oh, this one would. Yeah, so this one does satisfy the boundary conditions, and so does this one.
Does that satisfy the PDE?
Well, this satisfies the PDE, except you can't take that derivative of b of x ux. So that derivative does not exist at all points. So that's the one problem. Now you could say, well, in that case, you have a situation where it's a PDE with a discontinuous coefficient. Because certainly a PDE is allowed. A PDE does not have to have coefficients that have the right number of derivatives. It's really about the solution. But yeah, the boundary conditions here are not the issue. So the boundary conditions gave us these equations, which are satisfied by that or that, and then I threw this one in here to try to make the solution C1. I don't recall if, like in the MIT course, if there was any commentary about this case. I think the author there only presented this solution, just to illustrate, here's what a weak solution looks like. I'd have to check on that, but yeah, that's odd, to say the least. I just realized I've gone past time. So, whoops. Okay, this is what I get for getting myself in this sort of thing. That's so, as you all are GTAs, always prepare your shit. So you don't get into situations like this, as I like to do all the time. Because my next class is going to be totally spontaneous. I'm done for. Okay, so I'll pick up with the rest of this and one more example on Tuesday. Okay, so sorry about going late, but we also started late, so whatever. All right, hope we don't make you late for anything. Okay, let's stop the recording.